like. Here we are. So we tested on quite a large number of, you'll see along the bottom here, the protein length. These are quite small proteins, but it is worth remembering that a typical protein domain is actually around 120 residues. And what we've got here are in each bin of sizes, the column on the left is showing us success, and it's colour-coded according to fold class, and the column on the right is showing us failure. And so overall, in this large set, we solved about 40%. I just mentioned in passing those important Shelleck's criteria that we use, the Shelleck's correlation coefficient of greater than 25%. That's a very good guide as to whether your molecular replacement has worked. And we also verified that it could be refined and give a reasonable R3 as well. So the 2 key points from this are that as you go to larger proteins, your chance of success decreases. So you can see the bar on the right becomes larger, those are the failures, the one on the left is a smaller proportion. That's not surprising because actually the ab initio modelling is harder for larger proteins, so the models are less good and they work less well. The other important point to notice here is how well we did with all alpha proteins, so we solved about 80% of those, and how poorly we did with all beta proteins. And as you might expect, the mix alpha beta was somewhere in the middle. So there's a number of reasons for this. It's harder to model the all beta, but if you have a small all alpha protein, then you stand a very good chance of solving it with AMPOL. So just to give you an idea of what these search models look like, this is one of the successes. This is the structure we were aiming for. A bit of a delay on the mouse here. Oh, there we go. Sorry. So this was a set of original ab initio models. You can see them superimposed. You can see that this red part here agrees pretty well. The green and the blue parts are very divergent. And so we recognise this. We say we believe more in this red part. We don't trust the bit at the back. So we're going to truncate that off and leave us something smaller, hopefully more accurate. This we dealt with in this reliable side chain. I won't go into that level of detail. And this works. So this could be rebuilt by Shelleck's to give something that looks very close to the native, of course, and we could tell that from the statistics. And you may remember that the truncation operates across quite a wide search model size range, so sometimes we can get search models that range of sizes of search models and success across all of that range of sizes. So those were quite small proteins we initially tried with, and the limitation there is that the ab initio modelling only really works well at that point, up to around 150 residues. And as you remember, we struggled with all beta proteins. What we've done recently is exploit a new source of information from bioinformatics to help get better models. I won't go into too much detail. You've probably heard about this. It's called direct coupling analysis. So when you have a sequence of